All right, good morning, everybody. My name's Jim Schwartz. My role here at Beck is I'm Director of Research Agronomy and our Practical Farm Research Program. This morning, I'm going to talk to you a little bit about root reveal and our root reveal research. Now, one of the questions I get a lot is, why in the world did you guys start doing root reveal research? It actually began a few years ago when my youngest son, Stephen, was getting his master's degree under Dr. Fred Below at the University of Illinois. And Dr. Below had a student there, it was a PhD student named Scott Foxhoven. Now he's Dr. Scott Foxhoven. And Scott was working on understanding how root size impact nutrient placement in a corn plant. And as I began to have conversations with Scott, we began to wonder, could it be more than just root size? And we'll talk a little bit more about that in a second. So one of the other questions I get a lot is, well, what do you think root architecture will teach us? How will we utilize that on the farm? We believe, based on what we're understanding so far, is that root architecture will help educate us around three management practices that you will employ on your farm. One is population management. The second one is understanding stress management and placement. And then the third thing is around nitrogen placement, nitrogen rates, and maybe even nitrogen timing. So going back to Dr. Foxhoven's research, when he started that project, he had a number of assumptions about roots. And one of the things he started with as a theory was that there is a response to population and P and K. So think about it. P and K do not move very much in the soil. And as a result, roots need to be in close proximity to those nutrients. He also knew that as we increase population, root size decreases. So if we increase population, the root size decreases, and fertility, especially P and K, need to be a little closer to the roots. And we know that hybrid root sizes are different. Could we see differentiated responses from hybrids to P and K placement? So that was a theory that he had. And so I'm going to take about a 350 slide deck and boil it down for you in 2 slides to summarize his research. What he found was indeed that small-rooted hybrids responded better to population and fertility placement. Now let's think about this for a minute. We know that as roots touch underground, there's a signaling that occurs in the plant. Whether it's a biochemical or a root exudate, we're not exactly sure. But we know that as roots touch underground, those plants talk to each other and they say, I'm crowded, I don't like this. And as a result, it elucidates a stress response in the corn plant. So if that's true, as I increase my populations, a smaller rooted hybrid would have less root touching than a larger rooted hybrid. Now, we would say, we believe now, it's not only root size, but root architecture. But that was the first thing he found. And then the other point he made was that larger rooted hybrids have less response to increased populations and or fertility placement. I would say larger rooted hybrids, and again, we're going to talk about root architecture, actually have a negative response to increase populations. So summarizing his 5 years, this was his doctoral dissertation, he came away with 3 main points. Number 1, smaller roots require better fertility placement. Number 2, this one's key, and we'll talk about this a little bit later. We believe that roots and rooting could explain a lot of hybrid variability that heretofore we've not understood. I've been in the seed business 39 years. I cannot tell you the number of times I've recommended hybrid and it fails. And I'm like, I'm sure that was the right hybrid. Why did it not work? We believe that this might help explain some of that variability. And then also that a single hybrid's yield potential could be different than previously thought based on root size. And now we're going to examine root architecture as well. So this is why we started to engage in this process. We met with a young man named Dr. Chris Topp out of the Danforth Center in St. Louis, and he does a lot of root research on sustainability, nitrogen assimilation, and he showed us that he was growing cover crops in a certain manner. And so we came home, we asked him if we could steal the idea, and we did. And basically what we did is we took old chem totes, and we string them with 100-pound fishing line. We shrink wrap the tote, put OSB around it, strap it together, and we fill it with a product. And there's some bottles on the front seats. You are free to grab those and pass those around. We fill it with that product called Turfus. So if you ever go to a Cubs game, specifically Cubs game, right? And not Cardinals. If you go to a Cubs game, all right, and it rains and they throw something on top to soak up the water, that's what that stuff is. It's so nutritively, it has very low value, so we have to provide it with water and nutrients. And then after about R1 or R2, when root growth stops, right, we cut the plant off, we turn the water off, wait about 2 weeks, open the box up, and out the product flows, and this is what we have left. And as we began to do this, right, we started to see some amazing differences in root architecture. So on the left is a hybrid that we would say that's very much a horizontal root architecture. On the right, very much a vertical root architecture. Now, one of the things then we wanted to say was, okay, what does this mean? Imagine, for instance, the hybrid on the left. And you can see differences there in the boxes themselves. On the right is vertical, on the left is horizontal in those cages, okay? What if you no-till, and you've no-tilled for 10 years or 15 years? Do you believe that that hybrid, and you have nutrient stratification, do you believe the hybrid on the left might respond differently than the hybrid on the right? Maybe. What if you have a low nitrogen environment or a low water environment? Do you believe a hybrid that might have a deeper, more prolific vertical root system might respond differently than the one on the left? That's what we wanted to understand. So what we chose to do is we reached out to a young man sitting right over there. Raise your hand. That guy right there is doing his PhD research with Beck. His name's Sam Leskonich, okay? Sam and his team are doing this research at the University of Illinois, and we asked them to engage in a couple different projects. The first project was to understand, does surface area, mass, and angle, do those three things really matter as it relates to nitrogen management on your farm? The second thing that we asked them to do was help us understand how population management and root architecture interact. Those are the things we wanted to understand. So, I'm going to show you some data, because the first thing we had to understand is, are there differences, right? So we gave them 8 hybrids, and we classified them for those 3 things. First was surface area. So surface area, I'll give you a rough approximation. Think about if I have a big arm, one big root, versus a lot of smaller roots. That big root would actually have less surface area than those smaller roots, okay? That's partially an explanation. But that is the surface area of the roots. Interestingly enough, sure enough, the 8 hybrids, those are statistically significant differences. I took the numbers off the bars to simplify the graph. Statistically significant. Surface area. What about angle? So angle would be vertical, horizontal, and then something in between we would call it balanced. Sure enough, when you look at those numbers, those are statistically significant differences. There's 40-degree angle differences between those hybrids. And then the last one is mass. So just a mass, think of weight. It's a calculation based on algorithms that come from that box that I'll talk about in a minute, okay? But again, when you look at hybrids, what we learned is, yes, there are statistically significant differences. So Dr. Below has been a plant physiologist, I think 46 years. 46, 43? Sam doesn't know either, but it's somewhere in that neighborhood, okay? And as he was seeing some of these pictures, he had shared with us that he was shocked at the differences he saw. And if you've been a plant physiologist, one of the leading plant physiologists in the U.S. all those years, and you're shocked, that probably means there's something that we don't quite understand. So what Sam did was he created the SAAM rating. How convenient, right? So SAAM stands for surface area, angle, and mass, right? So those 3 things we just went through. So surface area, so you see 6128 is SNS. Smaller surface area, narrow or vertical angle, smaller mass. On your right, 6381. Larger surface area, wide angle, large mass. Okay? So we created these different characterizations. Those are the first 4. Here's the second 4 hybrid. You can see there are differences. So as we began this research, right, we want to say, can we characterize based on the architecture, and then can we use this SAAM rating to understand differences as it relates to nitrogen management? So let's see what we learned. Now, when we did this data, a couple things I want to call out. Number one, this is 1-year data, 1 location. I think it's 6 replications. 6 replications, okay? So we're gonna treat this with the appropriate caution, all right? We'll talk a little more what we're doing this year, but this 1 location with 6 replications. But what we also did was we took 3 different nitrogen rates. We took 120 up front, so that is to simulate a low nitrogen environment. We did 180 up front, simulate more of a natural nitrogen environment, and then we did a split application to understand how root architecture might respond to those different regimes. Interestingly enough, when Sam started looking at the data in the low nitrogen environment, what did he find? That vertical root architecture tended to respond better. Now, here's the interesting thing about that. Penn State's done a fair amount of work on this, and their data would mimic this as well. And I'll share some of that in a little bit. But Penn State data would say we tend to believe that vertical root architectures respond better in low nitrogen environments. That's encouraging to us because it says, yeah, maybe we're headed in the right direction. Now, split application. So now I've got large, wide, and I'm putting my nitrogen out in the middle of the road. Are there any differences? Well, interestingly enough, when you look at the differences, it shows us that the large, wide tend to respond better to culturing nitrogen in the middle of the row. Does that surprise you? Probably not. Now, I want to point out, look at the top, 6128. It had a good response, right? I'll make this statement. Anytime you deal with biological organisms, there will always be exceptions to the rule. I doubt we ever come out and say, here's a hard, fast rule, you can count on this. We believe there will be trends, but there will always be exceptions to the rule as it relates to corn hybrids. There just always will. That one is an exception to the rule, and that's okay. But what we're trying to see is if we can develop some trends to better manage the hybrids on your farm. Conversely, right, now I've got smaller root systems, and I'm side dressing out in the middle. What do I see? The hybrids that performed worse tended to be those smaller root mass hybrids, okay? It's kind of intuitive, okay? So, what are the key takeaways? Yes, we can categorize based on the SAAM rating. What would you have done if your name was like Joseph? Yeah, he doesn't know. So, at low nitrogen rates, right, those narrow-rooted hybrids perform the best. And then also, that large root surface area tended to respond better to split applications. Interesting. When I shared this data with our corn product lead, Craig Moore, we had been doing some internal work as well, because one of the questions we have to answer is, what impact does genetics have on this? Because genetics might rule all. So maybe we're just heading down a bunny trail that's not real. Interestingly enough, we have a couple hybrids that are closely related. Same family, okay? Very closely related hybrids. But the interesting thing is they have two completely different root architectures. So here's one, 6469, has a vertical root architecture, had a positive response to increasing population. Now think about roots touching, crowding the plants, right? And had a moderate response to side dress application. But now I want to show you a sister line with a horizontal root architecture. Negative response, very negative response. So the roots spread out, more touching, negative response to increasing population, and look at the response to side dress nitrogen. So I'm going to go back, vertical, sister line, horizontal, look at the differences. It's one example, but it's important to us. We're going to do more of these sister line comparisons that have different root architectures, but that's interesting to us because it may say that, yes, indeed, the phenotypic traits of the root architecture may be driving some of these responses. So the second study we asked them to engage in at University of Illinois was population response to root architecture. So back in 2014, I think it was, Dr. Barnhart, University of Illinois, had done some work and found that for every 1,000 plants we increase planting population, individual root size decreases 2.5%. Every 1,000 plants we increase planting population, individual plant root size decreases 2.5%. Let me ask you a question. What have we been doing to planting populations the last 20 years? On average, about 400 plants per acre. So if you do the math, over the last 20 years, we've decreased our individual plant root size about 1% per year, about 20% overall. Would that have an impact on how those plants access nutrients? Maybe, especially P and K that don't move. So we wanted them to dig into it. And here's the interesting thing. Guess what their data showed in 2024 at the University of Illinois? For every 1,000 plants you increase plant population, individual plant size decreased 2.5%. So again, we take encouragement from the fact that the data and the research is marrying up with other research in the past. So I want you to think, this is just a good visual. So 30,000 plants per acre, 42,000 plants per acre. Imagine root architecture now, and remember what we talked about the root touching, okay? Do you think that if I have 30,000 plants per acre and a vertical root architecture versus horizontal root architecture, would I get a differentiated response than at 42,000 plants per acre? How many times have we planted these hybrids at higher populations and they go, didn't work? And we go, well, I don't know, should have worked, why didn't it work? Maybe this is part of the explanation. And that's what we're trying to dig into. So when you look at the data that Sam and his team developed, okay, as we increase our populations, above ground plant biomass increases. That green line then is individual plant to plant root size. It decreases 2.5% for every 1,000 plants we increase. Now, because we're adding more plants, right, overall, our root mass per acre is relatively flat. But if you compare the orange to the blue, what we're saying is you're supporting a significantly increased amount of above ground biomass with the same, virtually the same below ground biomass, root size. So does that change how you have to fertilize? That's what we're trying to understand. But again, this was the key takeaway from that study, was that as we increase populations, above ground goes up, below ground virtually remains the same. So key takeaways, that 2.5% that we talked about, increasing plant populations, again, above ground biomass, but here's the one that I think is kind of the key to this. The hybrid with the large, wide SAAM rating did not tolerate higher plant populations. What did we show our internal data was showing? The large, wide responded negatively to the increasing populations, and that small, narrow may be better suited for higher populations. Pretty interesting stuff, okay? So what's next? What are we going to do next to continue to understand roots and root architecture? So this year, this right now, the Illinois team had taken those two different studies, the population and the nitrogen, squished them together, created a big study, and replicated it at multiple locations to get different soil types. Additionally, we've added a couple studies in practical farm research around fertility placement, root architecture, and then being a good Boilermaker, of course, I had to go back to my alma mater, and I asked Dr. Quinn to initiate a study on banding versus broadcast relative to root architecture as well. Now, one of the ways that we help get that SAAM rating is through this box. I still call it a crib box. They call it a crop box, corn root imaging box. And Drs. Bone and Grift at the University of Illinois had developed this technology, and as we were trying to understand this whole concept, we met with them because Dr. Foxhoven had used this tool to help characterize his roots as well. And we asked them, hey, would you guys build us a box? And they're like, well, we've never really done that before. But they agreed to build us a box, and that is our box over there that's lit up. And that's how we help create these ratings that we utilize for our root architecture. So I'm going to show you a quick video. These are some Purdue students. This is V7 corn, but I'll show you a quick video of how they do it. They take the box, put the plant on a spike. It's got multiple cameras in there. And then as it's rotating, it's capturing dozens and dozens of images that are going to help us quantify. Again, this is a V7 root, but in that amount of time, the hybrid's done, into the trash can, start with a new. The beauty of this tool is it gives us quite a lot of throughput to be able to quantify a lot of roots. Additionally, then, we've invested in some pretty high level of photography in order to take those cages now, basically digitize the roots, remove the cage, so that we can better understand some of these characteristics of the roots. So this is a great example. This is actually a horizontal root architecture, even though it's very massive. Look at the roots in that narrow profile. Conversely, this is very much a vertical root architecture, okay? When you look at that, that's what that allows us to do, to continue to understand a little bit better how those things look in their architecture, okay? Hopefully someday very soon that will be up on our website as well. Continuing, what's next? FMC had reached out to us. FMC has a lot of soil biological type products. They were curious about, could we maybe do some collaboration on some of their products? Well, we told them, said, hey, start with a bucket and just see what you find. That's pretty interesting results. So we're working with FMC. We're going to be testing some of their products in these cages. Additionally, there's a company called Sequesta had reached out to Beck. Sequesta is a gene editing company, but they only edit for one thing. They edit for roots, okay? And when I asked them, what's your theory? What do you wish to edit for? They said, we wish to edit your germplasm for deep vertical roots. They said, why do you wish to edit for deep vertical roots? And their answer was, because we believe those hybrids perform better in low nitrogen, low water environments, which what did our data show earlier? That's encouraging to us that you get some of those similarities. So Sequesta, we're working with them to edit some of our germplasm for vertical roots and see if indeed that is correct. I mentioned earlier Penn State University. Penn State University has done quite a bit of work with roots. They have isolated a gene for vertical roots, the one on the right, but on your right, they've also talked about steep, cheap, and deep roots. Steep, cheap, and deep. And if you go and dig into the Penn State data, what Penn State would say is, we want steep, cheap, and deep roots because they perform better in low nitrogen, low water environments. So that's an encouragement to us, again, to say, it seems to be marrying up with our research. Based on that, I asked Craig Moore, again, our core product lead, I said, Craig, go back and just do a meta-analysis. Craig has actually been digging and classifying our roots for about 8 years. And I said, Craig, go and do a meta-analysis of our plots. And so he went and looked at our 175 bushel or below plots. We would call those more of our stress environment plots. And when you looked at the data, interestingly enough, the vertical architecture tended to perform best in those low-yielding environments. Again, you start seeing these themes tend to repeat themselves. That's encouraging to us. Then I said, okay, what about the highest yielding? Interestingly enough, in the real high yielding, that balanced root architecture tended to perform best. Now, as you look at our entire lineup, we've classified all the hybrids. It's interesting. It's a direct bell curve. About 50% of our hybrids fall into the balance. 25% are horizontal, 25% are vertical. Now, one thing I want to point out here, as you look at that, you might go, well, I don't want horizontal. That may not be true. In fact, if you take nothing away from this talk, understand that there's no right or wrong root architecture. There's no good or bad. There's only placing them to match the practices that you engage on your farm. Because here's the thing. If you are doing something on your farm and I sell you a hybrid, you're not going to change the way you farm, right, based on that hybrid. So I better do a better job of placing that hybrid to match the specifics of your management practices to help de-risk and to help improve the odds of success. So additionally, we continue now every new product that we bring forth, we will characterize in a box and have that information available soon. So as I wrap up, I want to tell you a story about this hybrid, 5350BR. And it's an interesting tale that, again, we hope points to where we want to go with this. So this was a brand new hybrid that we released last year. This hybrid has the most vertical root architecture we've ever seen. I mean, if I took a 2-pound Folgers coffee can and cut the bottom, I could run it up and down, and that would encase the entire vertical root architecture of that hybrid. So we released the hybrid, all excited about it, did great in Minnesota, Wisconsin, and guess what happened after we released it? It didn't do very well. We're like, daggone it. Now, in the past, we would have said, well, out with that one, we'll get a new one. But my regional agronomy manager up in that area in Minnesota, he lives in Gibbon, Minnesota, he goes, Jim, let me do something. And so he took all the plots within a 100-mile radius of where he lived in Gibbon, Minnesota. And when he looked at those plots, sure enough, what did he find? Yep, 8 bushel below the mean. Not going to get very excited about a new hybrid that's 8 bushel below the mean, right? Except he then took that data and looked at either high nitrogen environment or banding fertility, whether it's wide drop or banded fertility under the rows. So those are the colored rows. And then the white is broadcast fertility. 22 to 23 bushel swing in performance. That's what we're trying to prevent in the future. This is 5 years ago. I would have gone, I don't know why it didn't perform that way. And the reason he knew to do this, right, was through our product characterization research that we just started last year. What we're doing is we're basically taking a hybrid, and instead of comparing it to another hybrid, now we're comparing a hybrid to itself. We're taking 3 different populations. We have a control, then we have 2 different fungicide timings, and then 3 different nitrogen rates and or timings. And what we get is about 21 data points on that hybrid. It's about 0.8 of an acre research per hybrid per location. It's very intensive research. But we did this on Nate's farm last year as we dipped our toe in the water. And here's why he knew to dig into that data. So look at the top. That's 180 pounds, 2 by 2 by 2. Then look at the bottom. That's 180 pounds, and all we did was we split apply it with a coulter. Vertical root architecture, split apply it with a coulter over here. 20 bushel difference. Look at the rate differences. 50 plus bushel difference. Okay? That's why I hired him to be my new product characterization research manager. I'm like, okay, you're smart, dude. You can do this for a living now, all right? So we have initiated now a new group at Beck's called Product Characterization Research. So it's PCR versus PFR. We're going to start running this protocol right here over all our hybrids. Very intensive, very time-consuming, but we want to understand better so that we can de-risk this performance variability on your farm to the best of our ability. So this year I would call it kind of a beta test. So we're doing Gibbon, Minnesota again. We're doing here in Atlanta. It's right across the road over there. Then we also went to our research farm in in Lafayette, Indiana. So that's more of a sandy soil off the Wabash River. So that will give us 2 geographically very closely related data points, but 2 very different soil types, and see if we can gain more understanding. So that's really what we're doing with PCR and root reveal research, because the goal long term is to start putting puzzle pieces with root reveal research and PCR research together to start de-risking decisions and eliminating failures on your farm. So my life verse is 2 Corinthians 4:18. If you're unfamiliar, 2 Corinthians 4:18 says, so we focus on the things that are unseen, not the things that are seen, because the things that are unseen are eternal, the things that are seen are temporary. When you think about a corn plant, right, we're trying to focus on the things that are unseen. And we're trying to learn and see if we can learn more about these corn plants. Again, put puzzle pieces together with our PCR research so that we can learn so much more that you guys aren't experiencing these failures like we had with 5350 moving forward. Last thing. A lot of folks say, how do you do that? What's that look like? So this year, in Greenhouse 10, so if you walk over to the biotech building, in 30 minutes, we'll do a live root reveal. So you basically walk to the biotech building, go in the front door, turn left. It's the very southernmost greenhouse. Here in 30 minutes, at 11 o'clock, we'll do a live root reveal. Take 15 minutes if you're interested in learning about how we actually do that and see the root reveal live. With that, thank you for your time. We're honored that you came and spent your day with us. So have a great day, everybody.